Okay. Okay. Hi, everyone. I'm Christine, and I'm here to present my automated process for expanding experimental CCS reference libraries. Here's kind of our toolbox. At PNNL, we have developed tools to aid mass spec efforts on various fronts, which are great on their own. But what these tools really do that is exciting is open the door for high throughput data processing towards building this amazing spaceship of tangible identifications from fully untargeted mass spec data. Our tools leverage the power of Python and its available scientific libraries that enable powerful data processing. For instance, our tool MSAC automatically calculates adduct masses given neutral parent compound masses, and we can use it to screen for a much higher variety of potential adducts than are realistically accessible using traditional means. But what I'd really like to highlight is our tool Demos, which is a powerful and open source data processing tool with multiple built-in utilities that are shown in this figure. Demos includes many functionalities and also a very accessible API that allow us to select which pieces we need for each particular data processing stream, and can also handle multi-dimensional mass spec data in 1D, 2D, 3D, or beyond. And our idea was to use the powerful functionalities of our tools to build our spaceship, which in this case is a fully automatically generated library of collision cross-section or CCS values based on experimental data. So to curate this library, we start with experimental data here in the form of IMS, MSMS, which we acquired for roughly 4,000 compounds, combined into mixtures of 10 or so compounds per sample under the listed conditions. In total, this results in about 6,600 data files, including intermittent acquisitions of adjuvant tune mix data to generate CCS calibration curves. Meant to do that. And to curate our library, we first use our software to identify mass spec features corresponding to known features. Then we use the adjuvant tune mix calibration curves to extract CCS values corresponding to those features. And finally, we can store these CCS values in some sort of library. However, a key question that may arise and generally arises whenever we apply automatic workflows is how do we validate our method? Touching on the previous talk, how do we know we're not just generating a bunch of junk? In other words, how do we know we're even extracting the correct CCS values? And the answer here is database matching against reference spectra in our case. So in order to verify assignments for each feature and corresponding CCS, we matched MS2 spectra to GNPS to down select for the correct IMS-MS feature. And this means that of our 4,300 compounds, we found that about 2,500 have some form of adduct data stored in GNPS, resulting in 3,700 reference spectra. A quick aside, GNPS spectra are stored as normalized collision energy, whereas our data is at fixed collision energy, which is somewhat problematic, but we compensate for this by combining results across all of our collision energies to approximate this, but it's an imperfect method. Back to our workflow, how do we construct this? It's a fully modular pipeline in Python using the SnigMake workflow management system. And we start with our spectral data, initially converted to MZML format from raw vendor format. Next, we pick the raw data to reduce the value, reduce the data to possible features, and apply our CCS calibration to get CCS values for these peaks. We then perform matching by first generating a target list of adducts using our MSAC tool and search for putative matches, and finally apply an SNR filter to remove low quality features. Finally, we pull MSMS spectra by first applying the offset correction described by Jess earlier, and then we use deconvolution to assign MS2 features to the MS1. And finally, we score these spectra against GNPS to validate the entry. And so our results are summarized here. So we have about 3,500 resulting entries. What I'll highlight is this represents 1,765 compounds, which may seem like a low number, but really in terms of the actual entries we have to compare against GNPS, we're finding over 70% of those matched fully automatically. I've also included some figures to summarize what those data look like here in terms of adduct types and the voltages where the NC has the best match to our fixed collision energies. Lastly, I wanted to really quickly show what these results actually look like. Here's an example compound that's been identified here as this MS feature. You can see the 2D and the corresponding 1D views of the data here. And these are what the fragmentation spectra look like in 10, 20, 40, and 60. And you can see here as well that the 40 volt here corresponds to the best match to the GNPS spectrum, which here on all plots is overlaid as the negative axis, whereas our real data is the positive axis. So that was all really fast. I'll just summarize our work. We built a pipeline to automatically extract CCS values from experimental data. We use this to process over 6,000 data files and curate our library of over 3,500 entries. And in the future, we'd like to analyze more data and in more dimensions. So I'll just include links to our tools here. Feel free to look them up, use them. We're really happy to answer any questions about any possible usages of these tools. We're very excited about them. And with that, that's the end of my talk. I'd like to acknowledge the people who made this work possible, including our software developers, particularly Sean and Jess. Along with me were the DEMOS development team, and Maddie, who developed MSAC, Tom Metz, our fearless leader, our collaborators at the Dorstein lab who supplied the compounds, and of course our chemists who acquired the data, as well as our funding sources. So thank you for listening to my talk.
Thank you.